Okay. I kind of prefer to make my ratios greater than 1 rather than less than 1. You've made the linear ratio 6 to 12. I would make the linear ratio, can't make it anything if my pencil won't write. Okay. And I don't know that this is that important, but it may be, just because you're going to be taking square roots and cube roots and everything. So my linear ratio, I would have made it 12 to 6, or 2 to 1.
Okay.
Which makes the area ratio what? The linear ratio is 2 to 1. What is the area ratio?
36 to 144.
Well, just the square of the linear ratio. Whatever the linear ratio is, the area ratio is it squared.
Oh yeah, so it's 4 to 1.
Okay. So if the area of the big triangle is 4 times the area of the little triangle, what's the area of the little triangle?
72 centimeters squared.
That's the area of the big triangle.
Oh,
BAT.
Okay, hold on. Sorry. 288 centimeters.
It's smaller, not bigger.
Oh. 18 centimeters.
There you go. Instead of multiplying by 4, you want to divide by 4.
Yeah.
Okay? So that takes care of that one. There's nothing wrong with the way you did it. It's just that when we talk about linear ratios here, if I have a linear ratio of 2, I have an area ratio of 4, what's my volume ratio?
2 cubed.
Which is 8.
Which is 8.
Okay. If I have a linear ratio of 7/6, what's my area ratio?
49/36.
And what's my volume ratio? It's 7 cubed over 6 cubed, right?
Yeah.
Okay. So that's really the only thing you really need to know about these ratios. Now, they can give the problems in varying degrees of difficulty, but here they are asking, what are they asking for? Is TR a linear measurement or an area measurement?
Linear.
Okay, so they want the linear. We need to figure out the linear ratio. They give us an area ratio of...
It'll be 3 to 4.
Yeah, the square root of that. So the linear ratio is 3 to 4. So if the little TR, or rather, if the big LA is 24, what is TR?
Is it, wait, so the linear of the big one.
So the little one is 3/4 of the big one.
Hold on, 4, 6, 18.
Good. Doesn't matter the geometry shape. The only thing that matters is whether we're talking about a linear measurement, an area measurement, or a volume measurement. Now, perhaps you haven't gotten to volumes yet. Is that coming somewhere on this page? No, maybe not. Maybe. I don't know. But it doesn't matter. If they want to start with linear and area relationships, that's fine. So I noticed that they are doing this exactly backwards of what I suggested. They're putting the small one always on top and the big one on the bottom. That's fine. I'm not going to argue with that. So my area ratio is 16 to 25. What is my linear ratio?
Um, 4 to 5.
So if my small one has a base of 4 and 8, what does my big one have?
I don't know.
Okay, to translate this, it means this ratio between that and that has to be 4 to 5.
Yeah.
So what's A going to be?
6?
5.
No.
4 to 5.
Oh, yeah.
If A was 5, that ratio would be 4 to 5, right?
Yeah.
Or I can take the reciprocal of that, 5/4, and multiply by this one, 4. And that tells me that the answer is 5. Okay? So A is 5. How would I get B?
By multiplying 8 by the reciprocal?
Yes. So it's 10.
Okay.
And notice that if B is 10, the ratio of the little to the big is 4 to 5.
Yeah.
Okay. The radius is a linear measurement. So the linear ratio is 3 to 5.
Yeah.
What's the area ratio?
9 to 25.
And if the big circle is 75 pi centimeters squared, what's the small circle going to be? Or how am I going to get it?
Well, it has, like, 75 is, like, third out of 5. Like...
Well, so all you need to know is that this S, the linear measurement of the big semicircle, is 75 pi.
Yeah.
Excuse me, hold on a second. Sorry. The area of the big circle, semicircle, is 75 pi.
Yeah.
The area ratio is 9 to 25, right?
Yeah.
So how am I going to get the area of the little circle?
Multiply it by the reciprocal.
None. This one we already have our ratio set up small to big.
Just multiply it by 75.
There you go. Which is 27. So the area of the little is 27.
Yeah.
Which is 9/25 of 75. Now, let's look at doing these maybe a different way. Not a different way, but a way that you won't have any doubt as to whether we multiply by the number or the reciprocal. If the area ratio is 9 to 25, then I can set up a ratio equation. 9 is to 25 as what is to what?
3 to 5?
Well, as the area of the little, which is the area of the little, is to the area of the big.
Of the big.
75 pi.
So you just cross multiply?
Well, you don't even cross multiply. You just multiply both sides by 75 pi. And that's how we ended up by just multiplying 9/25 times 75 pi. The answer actually was, sorry, I gave it to you wrong. It's 27 pi.
Okay.
It's easy to drop that pi. That's a very easy mistake to make. You've got to be a little careful about it. And the solution is not to convert that pi to a number and work with something other than 75. The solution is just to bring along the pi and make sure you put it in at the end.
Yeah.
Not make the mistake that I did where I left it out. Okay, so let's go to the next one here. The lengths of corresponding diagonals of two similar kites are in the ratio of 1 to 7. What is the ratio of their areas? What they mean is, there's one kite. This kite is similar, meaning what?
It's like,
Each angle is the same.
but the side lengths aren't the same.
No, they're not the same, but they are proportional.
Proportional.
In other words, if this is a 60-degree angle and a 120-degree angle, then so is this.
Yeah.
What makes them similar is they have the same angles. And it turns out that if they are similar, then their sides are proportional. If this is 1, this is 7. That's what the first statement says. The lengths of the corresponding diagonals. Now, what they really meant was, there's the corresponding diagonals. They're saying if the length of this big short diagonal, let me go back here and erase that 1 and that 7. If the length of that diagonal is 1, then the length of this diagonal is 7.
Yeah.
And in fact, for all linear measurements, there's a 7-to-1 ratio. If this was 10, that's 70. If this little piece here is 2, then that's 14, and so forth and so on. As long as you are comparing linear measurements, the ratios are going to be 7 to 1, or 1 to 7. It looks like they use small to large on every single problem. That's fine. So the linear ratio is 1 to 7. Let's write it like that. What's the ratio of their areas?
1 to 49.
Yep. As hard as that is to believe, it's true. This can be 7 times bigger than that, but this area is 49 times bigger than this area. The ratio of the area of two similar trapezoids is 1 to 9. What's the ratio of the lengths of their altitudes? So what did they give us? What kind of ratio?
1 to 9.
But it's an area ratio.
Yeah. So it makes like the linear ratio weird.
Not weird, it's the square root of that. In other words, here's the thing, here's the relationship. If the linear ratio is x, yeah, there you go. The area ratio is x squared, and the volume ratio is x cubed. This is the way it works. So if they give us an area ratio, and we want to get the linear ratio, we take the square root of the area ratio. Well, the square root of 1/9 is 1 to 3. So far we haven't gotten to volume, but maybe we will. Looks like we get to it in 11. To tell you the truth, I wish I would have had this piece of page with my last student, because the problems he started out with were linear, area, and volume, and he had quite a difficult time. And I think if I could have started out with just 2 dimensions with him first, he would have been better off understanding it. And that's what they're doing here. So far we haven't dealt with volume. We're just dealing with linear and area. So, number 7, the lengths of the edges of two cubes are in the ratio of m to n. What's the ratio of their surface area? The lengths of the edges, what kind of ratio is that? Is that a linear, area, or volume?
Isn't it just linear?
Yeah. Anything that's going to be measured in inches or meters or centimeters is linear. If you're going to measure something in square inches or square meters, then it's area. And if you're going to measure something in volume, you're going to be measuring it in cubic inches or cubic meters. So that's how you can tell. And if you were to measure the length of an edge of a cube, you'd get something in a linear dimension. It would be either inches or meters or whatever your ruler is. So if the linear ratio is m to n, what is the area ratio or the surface area ratio? Surface area is measured in square inches. So that's an area ratio.
Yeah.
What is it?
Don't we have to have m squared and n squared?
There you go. You don't have to have numbers. It's this. That's the area ratio. If I could turn it into a volume, my volume ratio would be this. Okay. Eight ounces of dough are needed to make a 10-inch diameter pizza. How many ounces of dough are needed to make a 16-inch diameter pizza? What are they giving us? Well, I mean the 10-inch and the 16-inch. What measurements are those?
Linear.
Okay, what is the linear ratio?
10 to 16?
Yeah, 5 to 8. We'll leave it as a ratio. What is 8 ounces? What kind of measurement is that?
Like a weight?
It is, but more importantly, it's a volume measurement, right? The more volume of dough that you have to add, the more it's going to weigh. So this 8 ounces, even though that's a measurement of weight, what they really are asking about is what's the volume ratio going to be? If the linear ratio is 5 to 8, area ratio, which is not pertinent here, but I'm going to list it anyway, is 5 squared to 8 squared. But the volume ratio is what we want. That would be 5 cubed to 8 cubed.
So 125 to, I don't know what 8 cubed is.
I think 8 cubed.
512.
12, yeah. So 125 to 512. That's our volume ratio. So how much dough am I going to need to make a 16-inch diameter pizza?
The 512?
Take the reciprocal of this ratio. Because, in other words, this ratio is the small to the large, right?
Yeah.
But
So
they've given us the small. So we need to multiply the small, 8 ounces, by the reciprocal of this ratio. If they had given us the big, then we would have just multiplied it by that ratio.
Yeah.
Because they gave us the small, we have to make it bigger.
Yeah.
Well, that number is 4 times bigger, virtually. So, in other words, if you have your calculator, go ahead and put that in. Here, I'll do it. You should always have a calculator in front of you whenever we're having...
I do.
Okay, go ahead and multiply that number out. 8 times 512 divided by 125.
$32.76.
Wow. 4 times as much dough to make a 16-inch pizza than a 10-inch pizza. That's pretty astounding, isn't it?
Yeah.
Yeah. Okay, 11. Similar three-dimensional objects. The volume of the smaller pyramid is 320, and the height ratio is 4 to 7. What is the height ratio? What kind of a ratio is that?
Linear.
They are asking us about volume. What is the volume ratio?
Times the cube.
What's
the cube.
What's the ratio going to be?
4 cubed to 7 cubed.
Yeah. That is 243, and that is 64. So there's our volume ratio. And give me the volume of the small one is 320. So what do I have to do to that to find the volume of the big one?
Wait, say that again, sorry.
Okay, so they give me the volume of the small one.
Yeah.
So I've got the volume ratio. So how do I get the volume of the big one?
Set it, the cross multiplier or whatever.
Well, you know what? There's almost an easier way to remember it. And that is, you either multiply by the volume ratio or the reciprocal of the volume ratio, depending on whether you're finding the small one or the big one.
Mm-hmm.
Well, I've been given the volume of the small one. What do I have to multiply that by to get the volume of the big one?
4/7, or just 7.
The reciprocal.
Oh. So 243 over 60.
Right. Notice that'll make a bigger number. If this was the volume of the big one, I would just multiply by 64 over 243 to find the volume of the small one. But since they gave me the volume of the small one, I have to multiply by the reciprocal, whatever that number is. Okay, here we have similar right cones. What information are they giving us? Wow, what information are they giving us? It's kind of hard to tell. Best I can see is this 3 is the distance from the center to the edge. In other words, the radius of the base.
Yeah.
And over here, the radius of that base is 12.
Mm-hmm.
So, what have they given us? They've given us a linear ratio, an area ratio, a volume ratio?
volume ratio?
No.
Or linear?
Linear. Just look to the units. If that's not squared or cubed, then it's a linear measurement.
Yeah.
What is the linear ratio?
Um, sorry, my dog's going crazy right now.
It's okay.
Hold on one second. Give me about 2 minutes.
Buddy, now my dog's going crazy.
Hold on. Hey, can we do this last problem and then wrap it up about 6:45?
Sure.
Alright, thank you.
Okay, if you look at this little one, if I look at that from the side, I see this triangle.
Yep.
The only measurement they've given us is that. If I look at the big triangle from the side, they've given us that and that. What is my linear ratio?
3 to 12?
Or 1 to 4?
Yeah.
They're asking about little h and big H. What's this side right here?
Isn't it?
It's a right triangle. It's a 3, 4, 5 right triangle.
So it would be, I know it, yeah, 16, because it goes 12, 16, 20.
Right. In other words, you can have a 3, 4, 5 triangle, or you can have multiples of 3, 4, 5. Well, this is just a 3, 4, 5 triangle times 4. Okay? So, little h is 4, big H is 16.
Yeah.
The volume of the large cone. Well, what's the formula for volume of a cone?
I don't know that formula.
When it goes to a point, it's 1/3 always. In other words, when you shave if this were a right cylinder, it would just be the area of the base times the height. The fact that it goes to a point, you lose 2/3 of that material. So the volume of a cone is 1/3 the area of the base, pi r squared, times the height. Okay?
Yeah.
So the volume of the large cone is 1/3. What's its radius? Radius of the base?
Squared, r squared.
Well, it's 12.
Oh, yeah.
So it's 12 squared, 144.
Yeah, 12.
And we figured out the height was 16.
Yep.
So there's the volume of the large cone. That number goes right there.
Yep.
Okay. The volume of the small cone, remember our linear ratio is 1 to 4. What's our volume ratio going to be? I mean, we can figure out the volume of the small. Yeah, we can figure. Okay, 1 to 64, exactly. The volume ratio is going to be 1 to 64. So how am I going to get the volume of the small cylinder? I got the volume of the big cone.
The opposite reciprocal?
No, I'm going from big to small here.
So it would be, I don't know.
Just multiply this volume by 1/64.
Oh, yeah, duh.
Yeah. If you're going from small to big, then you'd multiply it by 64, not 1/64. So
Alright.
it depends on whether you're going small to big or big to small, whether you multiply by the volume ratio or the reciprocal of it.
Yep.
All right. And then the volume, in other words, we can get a number for the volume of the small cone. Just take this number, divide it by 64.
Yeah.
But in terms of the ratio of the volume of the large cone to the volume of the small cone, that would be 64 to 1.
Yeah.
Finally, they switch it to big over little.
Mm-hmm.
All right, so we got through 12. Make a note.
Yep.
Now, for our next appointment, what are we going to do?
Probably some homework that I work on tonight.
I mean, are we going? I don't mean that. I mean, when are we going to do it?
I don't know. I'd have to talk to my mom.
Okay. Are we going to do it in person or online or?
Online maybe.
This one is canceled for tomorrow morning, right?
Yeah.
Yeah, that's what your mom told me to do. So there's my schedule. I've got a session tomorrow evening from 4:30 to 6:30, and I'm pretty much open every other time for the next 4 or 5 days.
Maybe whenever, 7 maybe.
And just do 7 tomorrow night?
Sure.
Want me to put it down? A little easier for me to do it than it is for you to go online and do it.
Yeah.
On 7, well, the next day is Thanksgiving, so we'll just work from there.
Yeah, we'll talk about
We're
it.
just going to do 1 hour tomorrow?
Yeah.
Okay, because if you want to split it up, maybe you want to do one in the early afternoon if you want to get in 2 hours. But that's between you and your mom.
Just 1 hour.
Okay, I will
Alright.
text you the meeting ID number tomorrow night at 7.
Alright, thank you.
All right, Alice, bye-bye.